Awesome, thanks. OK, so in traditional use of a signature scheme, the signing key lives on a single device. And pushing a button on this device is sufficient to be able to produce a signature under the public key. In the threshold setting, we split the signing key into a number of different fragments with, I'll call them SKA, SKB, SKC. And you can put these fragments on your different devices, let's say your phone and your tablet. And it's basically, it needs you to push buttons on all of these and have all of these devices be in agreement in order to produce a signature under the common public key. And it's an important requirement that this signature that comes out of the threshold scheme looks exactly like the one that came out of the regular way. So for instance, in a 3-of-n signature scheme, any consortium of 3 parties should be able to produce a signature. And at the same time, no 2 parties should be able to collude to force a third into signing something that they don't want to. Right, so in a full threshold scheme, an adversary can essentially corrupt every party but one. And ECDSA, which is the elliptic curve digital signature algorithm, was standardized by NIST, devised by David Kravitz, and has seen widespread adoption across the internet in all of your favorite protocols. A quick look at notation. The elliptic curve is going to be generated by capital G and is of order Q. And the secret values in the system are the secret key, which lasts for the lifetime of a particular setup, and an instance key K, which is ephemeral. The public values, which are visible to the rest of the world, are the public key PK and the signing nonce R. And so a quick recap of how ECDSA signing works. The nonce is the instance key in the exponent. And signing a message involves hashing it first and adding to it the secret key times Rx, which is the x coordinate of the signing nonce. And then finally, division by K, the instance key. And unfortunately, this division step is nonlinear, and this nonlinearity makes adopting ECDSA in the threshold setting somewhat difficult. There have been works that have tried to address this, and there have been some limited schemes based on PyA, starting with Mackenzie and Reiter, and more recent works on this by Gennaro, Goldfeder, Narayanan, and Lindell. And recently, works concurrent to ours achieved practical key generation and efficient signing for the full threshold. Works by Gennaro and Goldfeder use a PyA-based approach, and Lindell, Knopf, and Landalucci use an Elgamal-based approach. At Oakland last year, we presented a way to get ECDSA signatures in the 2-of-n case under native assumptions. That's assumptions in the same curve as the signature itself. And in this work, we extend our work from last year to accommodate a full threshold under the same assumptions. At a high level, our approach is built on top of 2-party multipliers. That's oblivious transfer, instantiated in the same curve as the signature. The advantages of this approach is that with OT extension, which requires no extra assumptions, a multiplication costs just a few milliseconds to execute. And the cryptographic assumptions that we need for this are native to the same curve. That's the computational Diffie-Hellman is hard in the same curve. And on the other hand, we incur a penalty in terms of bandwidth. That's a few hundred kilobytes per party. I'll talk more about this later. In contrast, using, let's say, homomorphic encryption like the other works use, it's somewhat heavy in terms of computation. And while it saves on communication, it can incur extra assumptions, for instance. Let's say PyA. Right, so we use a multiplier that we built in our work last year. And this multiplier, which we optimize, is secure up to choice of inputs. And it's a challenge to design some sort of consistency checking mechanism that makes sure that an adversary uses correct inputs on all the multipliers. And to enforce this, we designed a novel, lightweight consistency checking mechanism, which is unique to our protocol. And this works roughly by verifying shares in the exponent before they're even revealed in the CLIO. And this is pretty cheap. It costs only 5 exponentiations a party and about as many curve points to be transmitted. And that's quite light. And we show that subverting these checks implies solving the computational Diffie-Hellman problem. So if you believe that holds in the same curve as the signature, then our scheme is secure. Right, so the trade-offs of this approach, we avoid expensive zero-knowledge proofs. So for instance, for UC security, this becomes easier. And we avoid assumptions foreign to ECDSA itself. Like all of our assumptions are arguably native to the same curve. And using OT-based multiplication, like I mentioned earlier, is pretty light on computation, but more demanding in terms of bandwidth, specifically more demanding than homomorphic encryption. But we show a couple of use cases to argue that this is not really an issue in practice. we implemented our scheme and benchmarked it and found that our numbers are pretty good. They're an order of magnitude better than the next best concurrent work. Right, so our model is that of universal composability by Canetti with a static adversary and a local random oracle. And this is strictly stronger than any game-based definition that can be formulated for this problem, which is used by some other works in this area. And the functionality that our protocol emulates, which is formalized in the paper, is the obvious thing. It samples a uniform secret key, and it computes an ECDSA signature when enough parties ask it to. The only assumption that we rely on in our world is that the computational Diffie-Hellman problem is hard, and specifically in the same curve as the signature itself. And the network assumptions that we use are, we assume a synchronous network and an access to a broadcast channel. And we achieve security with the BERT. Right, so walking through our approach, first the setup. It's fully distributed and involves running a bunch of OTs pairwise among parties to run the base OT's floaty extension, essentially. And our key generation is done in the style of Pedersen, which is to have every party Shamil share its secret, a random secret, and to define the secret key to be the sum of each party's contribution. And then and ultimately, at the end of this protocol, every party verifies that they have a share on the same polynomial by checking in the exponent, interpolating in the exponent. Right, okay, so the first step of signing is to get candidate shares for the instance key k, its inverse, and k in the exponent, which is just the signing nonce. So the building block that we use for this is the two-party multiplier with full security that we had from last year and some optimizations. And one approach to get candidate shares for k and its inverse is to have each party start with multiplicative shares of k and its inverse and run a conversion protocol to get additive shares out of this. This costs rounds logarithmic in the number of parties. Alternatively, we could use the well-known approach of Barulan and Beaver to get a constant round protocol, and we're working on this for our journal version. Right, so the next step is to get a candidate for the secret key over the instance key, and this is easily accomplished with standard techniques from the literature, basically GMW. Then this is the sort of secret sauce for our protocol, which is to check relations in the exponent. And a note on what the challenges are moving from two to multi-parties. It's not obvious how to generalize the checks from the two-party setting. You don't need to take my word for it. And we, in the two-party case, rely heavily on the Diffie-Hellman key exchange way of getting a signing nonce, which we can't do when there are multiple parties, or it's going to be fairly expensive in terms of rounds. And yeah, see the paper for details. There are ways that we get around this. Right, so at a high level, there are three relations that need to be verified. That's candidate shares of the instance key, its inverse, and its inverse multiplied by the secret key. Right, so consider the task of, the technique at a high level is to verify each equation in the exponent, basically each relation between these three values, using some auxiliary information that's already available to the world. And the cost of doing this, as you'll see, are about 5 exponentiations and as many group elements per party. And this is independent of party count. Like, it doesn't grow with the number of parties, and there's no genetic zero knowledge that we use in this. So this means that you don't have to, for instance, run as many verifications as there are parties and things like this. Right, so consider the task of verifying the relationship between the sharing of k and its inverse. And the idea at a high level is to verify that k times k inverse is 1 by verifying that k times k inverse in the exponent gives back the group generator of the curve. And let's see an attempt at a solution. Right, so we have R, that's the signing nonce, visible to the rest of the world. And we instruct each party to multiply by R its local share of 1 over k, and to broadcast this value. And to give it a name, let's call it gamma I. Now we tell each party to verify that adding up these gamma I values gives back the group generator for the curve. Right, this can be verified, k times k inverse is 1. Right, so this doesn't work immediately, and to see why, we have to see what's going on under the hood. Splitting up k to its constituent parts, a contribution by an adversary, call that ka, and a contribution by an honest party, call that kh. We can see that if an adversary puts in some annoying cheat value, call it epsilon, into its contribution of 1 over ka, that's a cheat relative to its initial committed value, it induces some offset that's a function of the values that it put into the system itself. So as an adversary, I can put in epsilon and Ka and find the offset for the sum check protocol to be some function of epsilon and Ka and nothing else. And because I know both of these values, as an adversary, I can compute the offset and sort of undo my cheat quite easily. And the idea that we use to mitigate this cheat is to randomize the target. That is, at the moment, we're expecting the sum check to give some constant value. That's just the generator for the curve. And the idea is to randomize this multiplication that we do so that the target of the sum check is unpredictable. Right, so we compute phi over k instead of 1 over k, where phi is a uniformly chosen value. And we reveal phi only after the adversary has already chosen all of the values in the system. So he can't, essentially his behavior with regards to this check has to be independent of phi. So to see how this helps, let's go back to our attempted solution. Right, so instead of 1 over k times the nonce, we now have phi over k times the nonce. And to give it a name, let's call it phi, like capital Phi, as the target of the sum check protocol. Now, if we see what happens when there's an additive cheat in the adversary's contribution, the ultimate value that it's going to induce as an offset, specifically what the adversary has to compute in order to be able to get away with the cheat, is now a function of phi as well, which the adversary doesn't know when he commits gamma I. So this makes sure that essentially with probability 1 over the size of the field, the adversary can't get away with putting any kind of additive cheat in. Right, so that's how we verify the first relation. And I won't be speaking about this now, but please read the paper if you're interested. We use similar techniques to verify the second pair and the final pair of relations. And roughly each of these checks costs per party a couple of exponentiations and as many field elements to be transmitted in 2 broadcast rounds. But of course, when we batch these together, the costs amortize, and you can run these in parallel and things like this. Right, and the final step, once we verify that all the sharings are good, is to just broadcast a linear combination of shares, which is quite simple. So looking at the dominant costs for our protocol, we look at the dimensions of the number of rounds, the public key operations, and the bandwidth required. And we see that the setup protocol needs 5 rounds, about 500-ish public key operations for every party in the system, and 21 times the number of parties kilobytes to be transmitted. And the signing takes log number of parties plus 6 rounds to produce a signature, and only 5 exponentiations online, with the bandwidth of about 100 kilobytes transmitted for each party in the system. And in the journal version, which is in progress, we use the technique of Bar-Ilan and Beaver to get an 8-round signing protocol. Right, so we implemented a protocol with an implementation in Rust, and we benchmarked it with nodes on Google Cloud with a node to each party. And in the LAN and WAN, we ran our benchmarks in the LAN and WAN settings up to 16 zones, which I'll speak about in a minute. And to prove that our protocol is friendly to the low power setting, we ran benchmarks with Raspberry Pi devices, with 3 devices being able to sign in under 100 milliseconds. Right, so setup costs under 100 milliseconds for up to 8 parties and under half a second for 32 in the LAN setting. And signing costs under 30 milliseconds for 16 parties, and at the extreme end, under half a second for 256 parties. So our WAN benchmarks were run with nodes around the world, with the heaviest link being between Europe and India at about 350 milliseconds round trip time. And 5 parties across the US were able to sign in under 300 milliseconds, 16 parties with one in each zone of the world at just over 3 seconds, and 128 parties across the world in just over 4 seconds. So to compare with concurrent works, we looked at the LAN benchmark setting specifically because that's what they implemented as well. All figures are in milliseconds, and right, our work log times, which include network costs, are an order of magnitude better than the next best work, even in the low and high threshold settings. And we find the same to hold for setup costs as well. Right, so a quick note on whether communication is really the bottleneck. So consider a mobile application which is human initiated. That is, a bunch of people on their phones press a button to be able to get a signature. Right, so with, let's say, 4 people doing this, this is less than 4 megabits transmitted per party, which for a responsive application running on LTE is quite reasonable. It's well within its envelope. And on the other end of use cases, consider like a large-scale automated distributed signing with a number of servers rigged up together to be able to produce a number of signatures. That's what we're aiming to optimize here is the throughput, right? And just by computation cost, which may I remind you is fairly efficient for our scheme, like it's pretty quick. The throughput is limited to about 260 signatures a second in the low threshold setting and about 31 per second in the high threshold setting. And in both these settings, we need less than half a gigabit of data to be transmitted per party, and this is quite reasonable to assume that we can do this with gigabit connections and the like. Right, so in conclusion, we have an efficient full threshold ECDSA scheme with fully distributed key generation, and our paradigm is of producing candidate shares and verifying which checks in the exponent. And this costs just a handful of exponentiations, a few hashes, and some zero knowledge online, with no zero knowledge online, sorry. And we instantiate this with assumptions that are native to the curve of ECDSA. And overall, our approach is light on computation, but communication is quite practical for many cases, as we show with our benchmarks of our implementation. And thank you. I'm happy to take questions.
Any questions? All right. Let's thank the speaker again.